just like to extend a really warm welcome to everybody who's on the line. We're really thrilled to present our first webinar, our first research webinar, and particularly thrilled to have such an eminent NBCF-funded researcher to kick off the webinar program. So Professor Matt Trau is currently a Professor of Chemistry at the University of Queensland, and he's also Deputy Director and co-founder of the Australian Institute for Bioengineering and Nanotechnology. Matt is really an internationally recognised leader in the area of the interface between chemistry, nanotechnology, biology and medicine. It sounds very complicated, but it's really key to identifying new approaches to addressing problems in breast cancer research. And Matt is also currently the lead investigator on a 5-year national collaborative research program from the National Breast Cancer Foundation. So we're particularly proud and pleased that we've got talent such as Matt on board with our research programs. And tonight he's going to tell us a little bit more about his research into personalised treatment for breast cancer and maybe explain a bit about how it can improve survival for breast cancer patients. So I'll hand you over to Professor Matt Trau. Thanks.
Thanks, Alison. Thanks for a lovely introduction. So it's a real pleasure to be with you this evening via the internet. Thank you all for registering. Thank you all for logging on. I'll start with a deep confession, and the deep confession is I've actually never given a webinar before. So I'm sitting here staring at a laptop screen. I'm new to webinars, so if I make a mistake, if during a particularly awkward question I press a delete button and cut you off, please forgive me. I'm doing the best I can. My daughter also gave me a lovely gift. She gave me a little chest cold, so if you hear me coughing and spluttering, I think it's a great thing about this forum that there's no possible way I can infect you. So again, thanks all for logging on. So I want to thank the NBCF for the topic. The title of the webinar is Personalised Treatment for Breast Cancer. How can it improve survival? I think this is a very exciting area. It's an area obviously where our lab works on. I think the personalised treatment of breast cancer is something, or personalised treatment of cancer is something that we're going to see emerge to have a bigger and bigger impact in the hospitals in the next few years. In fact, personalised medicine as a topic overall is something that's being debated very frequently around the world, and it's something that will have, I think, far broader reach than just cancer. It will reach into many chronic diseases that human beings currently suffer. It will reach into the cancer, infectious diseases, things like Alzheimer's, diabetes, and etc. So it's a great topic. Thank you for choosing it. So what I'd like to do today is really two simple things. The first thing I'd like to do is to give you my own personal perspective about this space and a personal perspective about how it pertains to breast cancer. It's a very fast-moving space. One of the things that's moving it so quickly is that we're currently at this, I think, very exciting interface or inflection point where we see a convergence of areas like nanotechnology, engineering with biology and medicine. And there's fast-paced movement. And so I want to give you a personal perspective about where I think things currently stand, and then also a very personal perspective about where I think things are going to go in breast cancer treatment in the next 5 to 10 to 15 years. So that's item one. That's what I'd like to do during the introduction. The second thing I'd like to do, and I'm not sure if we'll have time to go into it in much detail, but I'm hoping I can give you just a snapshot of just some of the work that we're doing in my laboratory at the University of Queensland, which is at the interface. Again, it's this, I think, wonderful interface between the physical sciences world of nanotechnology, which is making tiny little gadgets, and you'll see some of those tonight, with medicine and biology. So that's the goal of the introduction, and I think we're going to open it up for questions, and I'm looking forward to the questions. So before I get on with the talk, one of the things I've learned about short introductions is what you want to do is you want to make sure, particularly for an evening lecture, to conclude on the first slide. So I'm going to try to do that. I'm going to try to give you the main take-home message, if you like, straight away. So the main take-home message, if you like, could come from a question. You can think, well, what is this personalised treatment? Why do we need personalised treatment for breast cancer? Who cares? Why is it important? Why is there so much discussion about personalised medicine? The simple way to address it is just to say, it's almost a very bland statement, but to say that, look, cancer is complex. And breast cancer is very complex, unfortunately. We all think about breast cancer as one disease, and unfortunately, that's not the way it is. Breast cancer is at least 10 different diseases. And I'll say that again to make that point clear, because it'll drive much of the discussion tonight. Breast cancer is at least 10 different diseases. And each of those 10 different diseases involve different parts of the human genome. They involve different parts of the human DNA. In fact, what's interesting is that many of the particular breast cancers have more in common with diseases like prostate cancer or ovarian cancer or skin cancer than with other breast cancers. This is one of the things that's really driving change, and it's been brought about with new fast sequencing technologies. So that, I think, in itself answers the question that because breast cancer is many different diseases, at least 10 different diseases, what we really need is powerful diagnostics to be able to see the difference between those diseases and treat them with the appropriate disease for the appropriate changes that have happened in the DNA. That's the conclusion. That's the big take-home message. That's what it's all about. And the bottom line is that until fast sequencing technologies, which have emerged really in the last year and a half, 2 years, mankind has never had this capability before, but we have it now, and we need to bring it into the hospitals. And so the key take-home that I'd like to leave you with, if you like, before I leave the first slide, it really is the conclusion, is that I think we're at this very exciting point. I call it an inflection point where these new very powerful diagnostic technologies are becoming cheap, affordable, able to scan cancers, able to individualize them. And I think we're at this point where, if you go back quite a few decades, the word cancer used to be thought of as a death sentence. There's been so much development now that it's not really thought of that way anymore. But I see that in the next 5 to 10 to 15 years, we're going to emerge into a new paradigm. And the new paradigm will be one where we think of cancer as a manageable disease. It'll be something like HIV. When HIV first came on the scene, it was thought of as a death sentence. It's not thought of that way anymore because we can manage the disease. Even though we don't have the magic bullet yet to cure HIV, most people can survive for very, very long periods of time on current treatment. So that's the conclusion of tonight's talk. What I'd like to do, whatever time I've got left in the introduction, is now start to back up some of those statements with some real data. So let me start by showing you the clinical data. I want to show 2 pieces of clinical data of what happens to patients when they are diagnosed with cancer. What happens to them when they enter our hospital system. So that's my first slide. I'll just see if I can get this to work. Here it is. So the first message here is that prevention is far better than treatment. And of course this is common sense, but the data really bear it out, that is that early detection is really close to a cure. What this slide shows, and I hope you can see it, I think you can see my arrow. These are 5-year survival statistics of patients diagnosed, and the left quadrant here is breast cancer. And the 5-year survival statistics of 0 to 100% survival are shown for when the disease is diagnosed. Is it diagnosed early, mid-stage, or late once it's spread? And the staggering feature is that for virtually all solid phase cancers, you get the same pattern of survivalship. The first thing that really stands out is, and I'm pointing here, these are the most modern statistics. This is really good news. The great news with breast cancer is that if we can detect the disease early, you can see with this purple line that for patients that are detected early, they have a 95 to 98% chance of surviving beyond 5 years. And in many cases, these patients will be cured of the disease. And I'm going to repeat that. In many cases, with early detections, patients can be cured of the disease. That is something, to be honest with you, that just keeps me up at night because it is an amazing statistic. Unfortunately, this is the end of the good news. The sad thing with cancer is that if we don't catch it early, and this is of course what sparked many of the early screening programs, mammography, et cetera, and you can see the results are continuing to go up. the sad thing, the sobering thing, is that if we don't catch the disease early, what happens is there is a free fall, and this happens for all cancers. There's a free fall in survivalship, where at mid-stage, where I'm pointing to now, and the cancer's starting to spread, the 5-year survival rates drop. And then for late stage, when the cancer, if the cancer is only identified once it's already spread right through the body, survival statistics go from 98% with a good chance of cure all the way down to 20% survival. And the really sobering thought down here is we currently don't have a cure in this area. This is the area that really needs new ideas, new treatment, new technology. And that's really one of the key topics tonight. I'm going to focus in on these patients here to see how they're currently faring. So the first take-home message on this slide is that we really need new technologies to detect cancers early. If we can detect, for example, I'm going to be talking about new nanotechnologies that are cheap, affordable, accurate, and we dream of them having the potential to detect cancer early through a simple blood test. That's what I call the mission to Mars. If we could do that, if we could achieve that with any of the gadgets that I show you tonight, that would change the face of cancer care. It would be something that is almost as powerful as a vaccine for cancer. The second thing is what happens for these patients that are detected with late-stage cancer. That's my next slide. And again, we're going to go to personalization here. So I'll just click here. So this is what currently happens with patients. If patients are diagnosed with advanced breast cancer, and you know, I'm sure everyone in the audience knows someone who's gone through this process. I certainly do. They are usually rushed to surgery. In breast cancer actually is the most advanced treatment process of all cancers currently. There is the possibility of personalization with hormone therapy, but basically virtually all patients will get chemotherapy, and we're all familiar with the chemotherapy story. The really sobering fact is that of all the patients that are treated with chemotherapy, if you then analyze who gets benefit from the chemotherapy and who doesn't, what the statistics will show you is that only a small fraction, about 20% of all the patients treated, derive any benefit whatsoever from the chemotherapy. 80% of the patients that are treated with the chemotherapy, that endure all of the process, derive no benefit from the chemotherapy. That's not to say that chemotherapy is bad. Chemotherapy is a lifesaver. But it's highlighting this issue that we don't have right now the diagnostic technologies we need to be able to discriminate these different populations. That's why I show it. In fact, there are two reasons why this occurs. The first reason why our batting average right now, and I should say this is a great batting average compared to where it used to be, and it's getting better every day. But there are two reasons why it's poor. One is that we're not very good at telling whether we've detected the cancer before it's spread. And so for most of these patients, they're actually cured by the surgery. They don't need the chemotherapy. The cancer's been removed before it's been spread, but we don't know that, and we can't take the risk. And so we need better tests, more personalized tests that can tell whether the patient is cured and doesn't need the chemotherapy, or whether they do indeed need the chemotherapy. The second issue, and this is really the topic of tonight's talk, is that this issue of complexity. Breast cancer, it's not one disease. It's at least 10 different diseases. And in the hospitals right now, we are not very good. We don't have the technologies to be able to tell the difference between those 10 different types. In fact, to be fair, it's only with the sequencing of the human genome and rapid DNA sequencing methodologies that we've only known in the last decade that breast cancer is this complex. Now, you might think, geez, it's taken a while to figure that out. However, the way I view it is that is a remarkable opportunity. What that means is that through these technologies, we're now really getting to know the details of the enemy in ways that we've never seen before. And let me show you how we visualize what the enemy, the cancer, is doing. So I've talked a bit about DNA sequencing, and so this is really one of the next take-home messages that I'd like to get across. And I think this is The rapid evolution of DNA sequencing technology, I think right now, is an absolute game changer. It is giving us, it's like the U-2 spy plane. It's giving us eyes in ways that human beings have never had on what the cancer actually is doing at the molecular level. And the amazing thing about this area is how quickly it's evolving. This is really driving the change. It's driving so much of the change, and it's powered by this area called nanotechnology. Nanotechnology is all about making very, very small things. And in this picture you see a chip. It looks just like a computer chip, and I'll show you the importance of that in one moment. So basically, what I'd like to sort of point out to you, if I can get you all to cast your minds back to the year 2001 when the first human genome was sequenced. This happened with great fanfare. I remember it very vividly. It was an extremely exciting day when the human genome was published in Nature. It was heralded as an advance as important as man walking on the moon. I feel that it was. The issue, though, is that this is a process, not many people realize this, that took mankind 10 years to achieve. To sequence one DNA genome of a human, 10 years, and it cost $3 billion with teams working across the world. So here's how things have changed in just one decade, or in 13 years. So in my laboratory right now, thanks to the miniaturization of this whole process, thanks to chips, these little chips, they look like computer chips that you see in this picture, the cost and time that it takes to do this has slashed in ways that one couldn't imagine. So, basically, what we see is that currently from $3 billion, the cost of DNA sequencing has dropped to $1,000, and this can be now done in 2 hours. This itself, I think, is an absolute game changer. It's something that now enables us, it's only been available in the last 1 to 2 years, and something that enables us now to look and interrogate cancers in patients in real time. In fact, rather than just seeing the human genome, we're able to look at the genome, the transcriptome, and the epigenome, which is, in a sense, a way of looking at both the ROM and the RAM memory inside the cancer. Now, the magic of this is this process is continuing. Whoops, I've clicked to the wrong slide here. Just bear with me. So here's some of the data. What's happening in this process, and this will continue to happen, is continuous miniaturization of this process to make these devices faster, cheaper, more convenient. And what we're seeing here is something that's very similar to what we've seen in the computer revolution. There's something called Moore's law in computer chips, which basically says that every 18 months a computer chip will be twice as fast and cost half as much. So here's a logarithmic plot of what's happened to computer chips over the past several decades, and we've seen this go from supercomputers to an Apple II desktop computer to ultimately things like iPhones. What's amazing is that the same process is now, gosh, sorry, I'm hitting the wrong slide here. I'm hitting the wrong button. Here we go. That if you plot what's happening to these DNA sequencing chips, this is the same logarithmic plot plotted over the last few decades. This technology is being developed at a faster pace than what we've seen in the IT space. So, we've seen supercomputers, desktop computers, laptops, iPhones. For DNA sequencing chips, things have gone much faster. So this area is currently exceeding Moore's law. Let me show you what this is. This is powered by nanotechnology. Let me show you what this is enabling. And so what we're seeing now is for patients that are diagnosed with cancer, we now have the capability. So in my lab, we use devices like this benchtop sequencer. This is one technology that is offered by 3 different companies. And we're able to, in real time, within 1 or a few days, get so much information about the individual genome, transcriptome, epigenome of each individual cancer patients. As I mentioned, this currently, I think, is an absolute game changer. However, the process of miniaturization is not going to stop. It's continuing. And so the next 5 to 15 years, what we'll start to see, and they're emerging already, is devices like these handheld devices, and devices, this is a glucose meter that currently allows, as I'm sure we're all familiar with, allows a patient to measure with a blood sample, a blood sugar reading. In the future, what we'll start to see is devices like this that will give detailed information of our blood to see whether cancer is on board, has it spread, what type of cancer is it, which type of cancer we might be using, and then once treatment is given, is that treatment being effective? It's a very exciting time. This is just some publications that our lab, through the project funded by the MBCF, has put out in the last few years in this space. We're very active in both using these devices, discovering new markers, and then also miniaturizing these technologies to make them more accessible to hospitals and patients. So I think I'm probably starting to run out of time. But let me give you a little snapshot before we flip over to Q&A about some of the work that we're doing. There's activity not just on the technology development side, but I want to just give you one snapshot about an area called epigenetics, which I think is now transforming not only our understanding of breast cancer, but is also giving us so many new molecular markers that we feel we could potentially use to diagnose breast cancer. So the way this works, it's difficult to explain it quickly, but I'll do my best. The way this works is, when I was in high school, I was told that DNA is comprised of 4 letters, A, T, G, and C, and all of the information in life is enshrined in 4 letters, A, T, G, and C. Computers have 1s and 0s, and DNA has A, T, G, and C. Well, it turns out that's not quite the case. There are actually 5 letters, and the 5th one is modified in real time. There's the 5th letter, which is called, one of the letters is called cytosine, and it can be modified with this little tag, which is called a methylation, a cytosine methylation. And if you look at the background of any one of your cells, what you'll find in the DNA, there'll be this sequence of these little methyl groups. Think of them as little tags, little stars that occur on the backbone of the DNA. And that changes with time. It's like the RAM memory in your computer, if that makes sense. Now, this is an area that was of esoteric interest until fast sequencing technologies have come about. In the last 10 years, it's become clear that it's these epigenetic signatures that are pivotally important in the aging process. They're pivotally important for stem cell differentiation. In fact, this is probably the mechanism that causes aging. It's probably the mechanism that causes stem cells to differentiate into things like cancer stem cells, which are important in cancer. And what our consortium has shown in the last 4 years is we've discovered hundreds of epigenetic mutations, these little methyl groups that are changed in real time within the genome. We found hundreds of these that are pivotally important in the creation of breast cancer. So again, this is an example of how the technology is, one, changing our understanding of breast cancer, but is now giving us new markers, because these methylated DNA markers are present in blood, they're present in biopsies, and they're great targets to try to detect by some of the devices that I mentioned. I'll just quickly show you, if one wants to read these, currently the way one reads these DNA methylation devices is you have to use expensive equipment. Cutting edge would be a machine like this that costs $400,000, and every sample costs about $1,000 to run. We do this in a research environment. However, as we transition this out to the clinic, towards the hospitals, we use nanotechnology to invent new chips like this one here. This is a new technology that our lab has invented just recently, where what we're doing is reading exactly the same DNA methylation information on a chip where the capital cost, the instrument costs $10,000 rather than $400,000, and each test only costs $10. We've published some of these, they've come out recently, and we visioned that, if you follow Moore's curve, that in the next few years this cost will drop to a device that will probably read this with an iPhone, and the test would be a few dollars. I think that's really what's needed for screening of the population and also to get uptake of these sorts of technology in a very cost-sensitive healthcare sector. I probably don't have time to talk about nanotechnology, but I'm going to give you 2 quick slides. The way this works, this is Nanotechnology 101, is that here is an example of how we use nanotechnology to make this cheap and more accurate. We use the fact that DNA, which looks like this, it's a double helix, it can act as a conducting wire. And so if we're able to make DNA that's either short or long, we can very easily and cheaply detect those mutation events that I mentioned a little bit earlier. So the chip that I just showed you, this is in the, if anyone wants to chase this up, it's in these publications. I'm not going to go through the details of how this works. The only point I want to make is that the heart of how this works is nanotechnology. This is one of the pixels on the chip right here, and all the pixel does is just pass electricity through this wire, and it is able to detect whether the wire is long, in which case the mutation is present and cancer could be present, or the wire is short, in which case the mutation is not present. So we're very excited about this technology, and it's something that we're moving forward in our grant. Okay, so let me wrap up. So what will the future look like? Here's the summary. I basically concluded on the first slide, but the current approach pretty much looks like this. For patients that are diagnosed with cancer, as I've mentioned, they're usually rushed to surgery, given chemotherapy, and there's some level of personalization, but not much. And at this stage, we currently don't have technologies to monitor to see whether that chemotherapy has been effective. Patients usually at this stage go home. Some are cured quite happily, but others have to wait to see until symptoms return. We feel that where modern medicine will move is to a regime that starts to look more and more like this, where there's much more diagnostic technology to try to pinpoint exactly which of the 10 diseases that I mentioned is active and which therapy we need to marry with exactly that particular disease. And then a monitoring of this as we go forward, particularly if the cancer starts to mutate. So there are opportunities there for preoperative treatment, and the key here is comprehensive molecular analysis performed before and during treatment, with optimal personalized treatment given to the patient. I really feel that with this sort of approach, which is going to the heart of what's causing cancer, is the way forward to convert cancer from what used to be a death sentence to a manageable disease. I've got some other things here, but I'm also conscious that we're running on time and we may have questions. So I might just finish there by highlighting our team. This isn't done just by myself alone. We have a very high caliber team, multidisciplinary team within our grant, which involves nanotechnologists like myself, epigeneticists, geneticists, pathologists, surgeons, oncologists as shown on this slide. And I'll finish by showing a thank you slide from just my lab here at the University of Queensland. Say thank you to the MBCF for the opportunity to present, and happy to take questions.
Lovely, thank you very much, Professor Trau. And now, everybody, the floor is open to you. As you can see, just once again, at the top of the screen, there's a Q&A section, right in the middle of the top of your screen. If you just click on that and type in your question, only you can see your question, but we'll be able to see all the questions that are asked. And it can be on the presentation you've just seen, or anything about breast cancer research in general. The earlier you get in your question, the more chance we have of getting to yours, and we will do our very best to answer as many as we can in the time we have, which is only probably about half an hour. So I'll now hand over to Alison, who will then moderate the next section of this webinar.
Thanks, Richard, and thanks, Matt, for a really great talk. While we're waiting for all these wonderful and very challenging questions to come through, I might start off with asking you just a couple of questions about your research. So, personalised medicine, particularly for breast cancer, would really be the holy grail. How far away do you think a test, a blood test maybe, for breast cancer, and not just for diagnosing breast cancer, but for treating breast cancer more accurately? How far away do you think we're talking before that will be realised?
Well, thanks, thanks, Alison, for a great, easy question to start with. Everybody asks that. So it's a tough one. I'd like to answer it with some generalisms first, if I can. I'd say that there are two things that we're targeting. I think the absolute holy grail is a blood test for early detection of breast cancer. If we can detect breast cancer early, you change the map, right, with a simple blood test, because, as I showed earlier, 98% survival for people that are detected early with huge cure rates. I would call that, Alison, the sort of the mission to Mars. Right? That's a very difficult one. It's a very difficult one to solve. I think it's achievable. It's a difficult one to solve. The personalization one, which I referred to, of somebody's diagnosed with breast cancer, which therapy do we use to personalize? I'd call that the mission to the moon. And I think we're very close to walking on the moon, is my perspective. I mean, I'm just amazed. My perspective on it, I'm just amazed at just how fast this field is moving. Now that we were able, for the first time ever, to read cancer, to see every molecular detail of what the cancer is doing, it's really opening up the field. And I see that the personalization is something that's already starting to be trialed in the clinic. It's too expensive now. The current sequencing technologies are too expensive to be broadly available to the public, and they still have some major accuracy issues. They're a bit like the first Apple II computer, Alison. That's where I put it. Everybody said, well, what good is this? What would you do with it? But then look what happened to the Apple II computer in the next 5 years. So on the personalized therapy, I think in the next 5 years, starting from now, I think we're going to see really strident changes of really sharpening the way that we personalize and manage cancer. And I think that some of the main barriers there will be translating this in the clinic and just cost. How do we pay for all of this? Where nanotechnology is needed to drop the cost. On the early detection, that is the holy grail. We have so many biomarkers right now where people believe that these are the markers that are the sentinels for breast cancer. But we need to test them. We need to do the clinical trials. It's called prospective testing, where you track lots of women. And actually, we have, coming to the University of Queensland in July, Dr. Leroy Hood from the Institute of Systems Biology, who's running one of the largest prospective clinical trials in the world, 100,000 women, where he wants to track samples before patients get cancer, so that we can really find that needle in the haystack, that marker or several markers for the early detection, and achieve the mission to Mars. That one's hard to put a time frame on, Alison. I think the clinical trials are something that will delay that, but I believe it is possible, and I think it'll happen. You never want to give a deadline. I think with the pace of change, I see it as something that will be emerging in the next 1 to 2 decades. I hope that answers your question.
Yeah, fantastic. Thanks, Matt. Now, I've got a couple of questions that have come through from Tracy, which I might sort of ask at the same time. She asks, how will this approach help those patients that have finished active treatment? So maybe, how will this be relevant for patients to maybe see their long-term prognosis, Tracy? I'm thinking maybe that's the tone of your question. How can we track in those patients that have finished active treatment, maybe giving them some information about recurrence or the long-term prognosis? And her second question, which is kind of related, I guess, is would it soon be possible, if chemo is only helpful for 20% of patients, would it soon be possible to know if chemo is worthwhile or not? She says, I would hate to have gone through chemo for no need. And I think, obviously, Tracy's raised a really important point here, that if we can understand which patients are going to respond to chemo at the outset, we're in a really powerful position to be able to determine who has to go through the real horror and rigor of chemo and who doesn't. So a couple of questions there for you, Matt.
Well, Tracy, thank you for two really poignant questions. So the first one about recurrence and monitoring is something that's very much in our sights. And I think that is an area that these new technologies will attack almost immediately. If you think about it, so at the moment, because we haven't had those technologies before in the clinic, they just didn't exist before. We weren't able to track, changes in the blood that would occur if the cancer had recurred. So what we're targeting is, let's just look at the progression of cancer. So let's say, for example, the chemotherapy has occurred and it's failed, right, which happens. So if it's failed and the cancer is spread, as the immune system kills those cancers or those cancers die, they often release DNA molecules into the bloodstream. And so an area that we're targeting is to use exactly these technologies to probe into the blood after chemo to see whether we can see the earliest signs of those cancer cells recurring, or to give us an indication about, if the chemo has failed, if we've hit the wrong part of DNA with the medication, let's quickly change it to a different medication that might hit the right bit of DNA. It's a bit like think of it like ASIO. Having the intelligence of what the enemy is doing will allow you to be more effective in your offense. So that's one of our key goals. It's something that's not in the hospital now, but I think it's an area where these new technologies will become very prominent. It's very much in our sights. And I think it's also an area where we will see strong change in the next 5 to 10 years. The chemotherapy one is spot on. I mean, that's an issue that, to be, again, perfectly honest with you, it keeps me up at night. I mean, I think with these new technologies coming through, it's our duty almost to get these into the hospitals, to find ways that we can utilize them, and to improve the batting average. It's not a simple process. There's no magic bullet here. There's no guarantee that the first time we start running these, and we're running them now, to be honest with you, we're actually running the sequencing experiments now with patients doing chemo before, after, and trying to see whether we could even predict the batting averages. But that is one of the holy grails, Tracy, and those two issues that you raised are right on our radar. That's exactly what we're targeting.
Okay, thanks, Matt. We've got a question come through from Mary. Mary says, we've heard a lot in the press recently about breast cancer and about focuses on other cancers. How relevant is this technology, which is obviously very focused in breast cancer according to your talk, how relevant is this technology going to be for other cancers? Thanks, Mary.
Thank you, Mary, for a great question. I think it's very relevant. The bottom line, DNA is DNA. So if you can read DNA for one cancer, you can read DNA for another cancer. It's exactly. And I think not only will it be relevant for all cancers, I think the way that we think about cancers is going to change. I think at the moment we think about, well, it's breast cancer. It's breast cancer, or it's ovarian cancer, or brain cancer. I think in the future we'll think about particular parts of the DNA. What's the molecular mechanism? We'll talk about the HER2 positive pathway, or the progesterone pathway, which might be present in prostate cancer and breast cancer. We'll talk about if you think about it. I think about it like viruses that happen on my laptop. I had one this morning, actually, and the computer technicians, the first thing they did is they scanned the hard drive to figure out exactly what the code was, and then they bombarded that code to erase it. So I think the future will be, what chemo does is randomly bombard the hard drive, hoping that we'll kill more virus sectors than healthy sectors. What the targeted approach does is to find out exactly what's gone wrong and hit just that. And that'll be applicable right across the board to all cancers.
Great, thanks, Matt. So we have another question from Alison. Not me, another Alison.
Another question from you, Alison?
No, she asked, with early detection and BRCA testing, what alternatives could be available other than surgery? So I guess your talk's really focused on early detection, it's focused on potentially prognosis, etc. But how can you use these technologies to really get alternative ways of treating breast cancer other than surgery?
Yeah, that's a great question. So there is a big debate on the BRCA area right now. So I'll just say that where our lab is moving, it's just my own personal view, and this is just a personal view, is I would rather have much different approaches, or I'd rather have better alternatives than the surgery. So, of course, was it Angelina Jolie is the famous example of someone who's BRCA positive and chose to do preventative surgery. Now, if you could imagine that if we had that mission to Mars accomplished and we had a simple, cheap blood test that would able to scan for breast cancer, so that if it occurred, we caught it early enough to cure it, then I think that would remove the need for preventative surgery. We obviously don't have that now, and so this is a very difficult dilemma for many women, many patients. But imagine if we did. Imagine if we actually did have something that was as simple as one of those diabetes blood tests that one could scan. You could scan your blood every year, every 6 months, and if it's not there, I don't have to worry about it. If it occurs, it's occurred earlier. It's occurred early, so I can be cured of it. That's our dream, but currently that technology doesn't exist.
Okay, great. Thanks, Matt, and thanks for the question, Alison. So we have another question from Mary. She says, I'd also like to ask about BRCA1 and BRCA2 preventative treatments with tamoxifen. I think Mary's referring to, actually it was some NBCF-funded research which showed that giving the anti-hormone treatment tamoxifen to patients that are at high risk of breast cancer, so BRCA1 and BRCA2 carriers, can actually prevent breast cancer from occurring in the first place. And Mary asks how concrete the outcomes are with tamoxifen as a preventative strategy, given that usually tamoxifen is a 5 or 10 year treatment plan. So typically patients with hormone-positive breast cancer are on tamoxifen for 5 or 10 years. What are your thoughts on using tamoxifen as a preventative strategy for BRCA1 and BRCA2 patients?
Thanks for the question. It's a tough question. So I've got to point out that I work in the area of cancer and breast cancer. I'm not a medical practitioner. I'm not an oncologist. So I'm aware of the work that you've just described. In fact, one of our collaborators, Professor John Forbes, is, I think, a principal on, I'll just put him up actually on the slide. He's a principal and a world expert on, this is John here, he's at the University of Newcastle. He's actually one of the best surgical oncologists in the world. John, I know, is very cognizant of all of the issues to do with this preventative treatment. I've seen some data that looks interesting. I wish I could give you a better answer, but I'm not qualified to answer that question. I have to defer it to someone who is a research oncologist. Okay, well maybe I could, although I'm not a research oncologist, Matt, but maybe I could tackle that a little bit. Only from the perspective of knowing what NBCF is currently funding in that area. So as I mentioned before, we have funded a project based at the Peter MacCallum Institute, which has really led the way in looking at the use of tamoxifen as a preventative strategy rather than as a treatment plan. But another project, a very interesting project related to tamoxifen that we're currently funding in WA, is looking at really how does tamoxifen actually get used in the real world as opposed to in a clinical setting. So we might see that there's clinical guidelines. There used to be 5 years of tamoxifen for hormone-positive breast cancer, a 5-year treatment with tamoxifen after the end of chemo. Now the latest studies from clinical trials are saying that 10 years of tamoxifen is really valuable. But this study out of WA is really interesting because it's looking at not in a clinical trial setting but in a real-world setting, because we know that tamoxifen has really significant side effects. Many women experience quite significant side effects of using tamoxifen. So how are women actually using tamoxifen in the real world? Are they using it for 5 years? Are they using it for 10 years? And how is it really being used, and how is that impacting on outcomes? So some really interesting research in that area, and I think that's maybe what Mary is raising in her question. It's all very well doing these very important studies in a clinical trial setting, but how are these drugs actually being used, and how effective are they
in the real world setting. So that's a study that's currently ongoing in WA, and hopefully we'll be able to report on the outcomes of that in due course. So hopefully, Mary, that addresses your question. We've got another question from Alison.
There are a lot of Alisons on tonight, Alison.
There are. This is the same one that's not me. She asks, is it possible to use DNA markers to target chemotherapy to attach directly to cancer cells in a similar fashion to anti-hormone therapies like tamoxifen? So can we actually use the DNA markers to really, I suppose it's like this magic bullet concept, to try and get the chemotherapy right directly to the cancer cell?
That's a really great question. I go to a lot of, I'm lucky enough to go to a lot of nanotechnology conferences to try to keep up with the field, and I'd say probably about 40% of the research that I see is trying to do things like what you've just described, Alison. That's the Alison that asked the question, not Alison who's moderating. And I think there is some incredibly exciting research being done across the world where people are doing the sort of things that the trick that you've described. They're using nanoscale, very tiny miniaturized gadgetry, where they attach the drug to the gadgetry that will go in specifically specifically hit exactly the cancer cells, and leaving alone the innocent cells. Because of course that's one of the problems with traditional chemotherapy, that it kills often, most cells. It just happens to kill the cancer cells more often than it does the healthy cells. And so this smart bomb approach, or this nano laser guided missile approach, is really getting attention, and there's a drug called Abraxane that uses a different approach, but it's a nanoparticle drug which has been FDA approved, already on the market. There's another one that's I think it's doxorubicin, which a friend and colleague of mine, Alberto Gabazon from Israel, developed, which is it's a liposome nanoparticle chemotherapy that is the same sort of idea, where you put the drug, the bomb, if you like, into a little nano capsule and get it to go just to the cancer cells and not to the others. It's an extremely active field, and we're seeing, rapid advancement in that space as well. Alison.
Great, thanks, Matt, and thanks, Alison, for the question. We've probably got time just for another couple of questions, and while we're waiting for those to come through, maybe I'd ask you about cost, because I think you referred to it a little bit towards the end of your talk.
Yeah.
But really, just playing devil's advocate for a moment, it's wonderful having these terribly sophisticated technologies, these nanochips and laboratories on a chip, etc. But really, if they're going to be used and taken up and have some utility in the clinic, they have to be affordable. And we already know that there are many issues about new targeted therapies for breast and other cancers coming out, but they're just, really, really so expensive that it really almost leads to a two-tiered system where people can afford treatment or they can't afford treatment. So is this something that you really consider at the beginning of your research, that cost is a really important endpoint? And if so, how do you manage the potential cost of these therapies?
Well, thanks for the question, Alison. That's a great question. It's something that, so I'm a technology developer, and, so my views are biased from that standpoint, but I think that is absolutely key. From what I see, at the moment, what we hear about in the news every day is, in every Western country in particular, is the rising cost of healthcare and the constant and unrelenting pressure to minimize that cost rather than increasing it. And so the point, the question that you ask, Alison, I think is spot on the money, basically, that whatever technology that we might invent here, if it is not going to reduce the cost, it won't even get a moment's earshot. And I really think that nanotechnology is the answer here. The ability to miniaturize, and we've seen it already with whole genome sequencing. In 10 years it's come down, or 14 years it's come down from $3 billion to $1,000. And so it's not enough, and at the moment, it's sort of within reach of getting into the hospitals, because for the sequencing that we do now, it costs several $1,000s per patient, which is amazing. It's better than $3 billion, but for a modern healthcare system, it's impossible. There's no health minister in the Western world is going to allow a test that's going to cost $1,000 per patient that will require monitoring. So that's why we're focusing our research at two areas. One is we want to show that this stuff works with the existing, what's available now, which is the current sequencing methodology, and we're getting some really fascinating results there in the clinic now. At the same time, we're conscious of exactly that issue. We want this stuff to be used. So we're developing the nanochips that I described, and I showed you one cost reduction already, where these have to drop. And I think the cutoff mark is really at about $100 a test. If you're not below $100 a test, you're just not going to make a dent here. And it's not just the dollars of the cost. It has to be something that's sort of plug and play, that is automated enough so it can be used in the existing pathology labs before it'll make a dent. And so we're focusing our work exactly there for those reasons. Anyway, does that answer the question?
Yeah, I think so. That's great. Thanks, Matt. And we've just got time for one last question, which has come through from Debbie. So thanks for your question, Debbie. She asks, what we've heard tonight in regards to what the next 5 years may bring in methods of advancement in early detection, how long do you foresee the Breast Screen Australia program being effective and around for? Great question. Thanks, Debbie. So, Matt, over to you.
That's a great question. So, thank you for that question. We have a research proposal in the system right at the moment, actually, where we're very interested to trial some of our current systems that we're running, where we're able to extract DNA from blood and sequence. I talked about the circulating DNA in the system, that cancer cells, for lack of a simpler way of describing it, they spew their guts out into the bloodstream, and there are DNA messages there that we can read. So I should have probably explained that a little bit more eloquently than that, but nonetheless. So we're very interested in running a trial where, in parallel with a mammographic screen, a blood test is taken, and we have a crack at it. So that to see whether we can augment, because the mammography, I think, has had a huge impact in survivalship because it's improved, but there are a lot of false positives, and it misses a lot of cases. And so we'd love to start looking at seeing whether some of these technologies that are still a bit expensive, in the thousands of dollars, could, if run in parallel with mammography, could could improve the performance of mammography, and at the same time try to drop the cost. And then we want to start that process to improve performance so that the batting average of mammography goes up. We basically add more information. And then what we'd like to do is, if we could run that for a number of years, and if we see that the predictive power of the blood test is better than the mammography, well, then you might just drop the mammography. But that will take data on a lot of patients and a lot of people. When will it happen? These are really difficult questions to answer, and I'm also conscious that it's really important that we as scientists don't overpromise on some of these things. These things do take time to develop. I think it will happen. I think in the right setting, I think the augmentation will happen first, and then eventually, I like to think that in the next decade or so, depending on how quickly the data comes, we might be able to drop mammography and transition to molecular tests. I hope that's a sufficient answer.